think the waiting room is disabled, so everybody should just be able to join. Okay. Everybody should be able to see my screen here in a second, or at least my iPad. Then find my OneNote. There it is. All right. Give me 1 second, guys. My computer has frozen. Is everybody able to see my OneNote?
Yes.
Okay, cool. We're just gonna have to make do here for a second. All right. So while I'm waiting for my computer to unfreeze itself, we're gonna work through a couple of these problems that I have highlighted here. We're gonna start with substitution. And since we've got a decent crowd, you guys are gonna help me solve these. So again, like I said, this is a substitution problem. And so at first glance, what would be our initial approach?
To define u,
Correct. So what would our u be?
it's gonna be 2 plus x4.
Cool. So we've got u equals 2 plus x to the fourth, meaning our du equals 4x to the third dx, meaning dx equals du over 4x to the third. All right, and then so substituting that back in, I'm going to go ahead and substitute in u for this term here, and I'm going to substitute in my dx term here. Computer increase. Nope, doesn't look like it. All right, so rewriting this integral here, we've got the integral of x cubed square root u, and then substituting in dx, I've got du over 4x cubed. So what's the next step we do here?
I'm gonna integrate now.
Before we integrate, what do we do?
Move the 4x cubed to the front.
Okay, so you're saying I do this. Oops, not in red. So I've got x cubed over 4x cubed square root u du. All right, so then we can cancel these terms. And then I'm going to move this outside, making this 1/4. So then we get 1/4 integral of square root of u du. All right, so what's the next step here? All right, I'm gonna go ahead and evaluate this integral. And the way we do that, move this over so you guys can see. Again, I'm gonna add 1 to the power and then divide by this new power, 1/2 plus 1, which gives me 3/2. And then if I bring this fraction out of the denominator, what do I get?
2/3.
Perfect. So then now rewriting my integral here, I get 1/4 times 2/3 u to the 3/2 plus c. And then we've got 2 more steps to finish this up. What would be the first step we do?
Well, we can combine the fractions.
Cool. So we get 2/12, which is really 1/6. And then I'm going to substitute our u term back, giving us 2 plus x to the 4th to the power of 3/2. Oops, sorry. Halves plus c. We agree?
Yes.
Cool. Give me 1 second. My computer unfroze, so I'm going to hopefully get back onto my computer. All right, in the meantime, I'm going to go ahead and show you all this next problem. So that way we can start thinking about our approach. This is another substitution problem. What would our first step here be?
To define u as well.
Right. So what's our u?
Sine of x.
Nice. Very nice. So u equals sine of x. Du, what's the derivative of sine?
Is cosine x.
Nice. Cosine x dx. So dx equals du over cosine x. Okay, rewriting our integral. Get cosine x times cosine of u. And then substituting in my dx term, I get du over cosine x. All right. So the next thing I can do here is I can go ahead and just cancel these cosines because we have a fraction. So this is technically in the denominator of our function. And then rewriting that gives me cosine of u du. And then what is this integral?
Negative sign.
Minus sign?
Oh no, it's just sine, right?
Okay, awesome. So just to clarify, give me 2 seconds. I need to mute myself on my iPad. Cancel. All right, so I can hear you guys on my computer, which is great. So with trig, specifically sine and cosine, I use this nifty little chart to kind of help me remember in the direction I need to go. I've got sine of x, cosine of x, negative sine of x, and then negative cosine of x, because it'll always repeat. And if I go down the chart, I'm taking the derivatives. And if I go up the chart, I'm taking the integrals. So just a little food for thought, something you can use. I definitely recommend it. I still use it to this day. Put that up here for y'all. Okay, so you said sine of x, correct?
Yes.
Cool. So I've got, oops, not the integral. Sine of x, sine of u plus c. Substituting my u back in here, I get that this equals sine of sine of x plus c. We all agree?
Yes.
Cool. Chat and make sure nobody is in the waiting room. Shouldn't be a waiting room. Okay, awesome. All right. Moving on to the next one, we have a bit of a definite integral here. So the first thing I want to do, we know what we need to do. We've got u equals du equals and dx equals. So go ahead and fill this in for me. What do I get for my terms? Oh, can you guys still see my screen or no? Probably not, right?
No.
Sorry. Alrighty. So what's my u term? Very
Cosine.
nice. Thank you, Bianca. Thank you. Yep, that was correct. Cosine of theta. All right, and then taking the derivative, I get negative sine of theta dx. Yes. Actually, sorry, this should be d theta. D theta, and this should be d theta. So then d theta equals du over negative sine. Okay, substituting all of that in. What is the next step here? Once I substitute here from 0 to pi over 3 sine of theta over u, and then I get u over negative sine of theta. Next thing we can do, I'm going to go ahead, cancel these two terms out. But don't forget, we still have this negative sign here. So I'm just going to pull it out and put it in front of my integral. So then we get the integral from 0 to pi over 3 of du over u, or I guess I'll rewrite this in a more standard form. 1 and du. So what's next? What do we get for this integral?
Is it going to be ln u?
Nice, very nice. We get natural log of u. And so first, I'm going to ask, how do we want to approach this next step? Because remember, we have our bounds here in terms of theta, but we just took an integral with respect to u, so we can do one of two things. We can change our bounds, or we can substitute our u back in and go from there. What do we want to do?
Change the bounds.
Nice. So how do I do that?
Plug it in the bounds into cosine.
Okay. So if I plug in, oops, I'll do this in red. If I plug in pi over 3, what do my new bounds become? And then 0. What do I get for my upper bound? If I substitute, I'll clean this up real quick so you guys can see
Say
what I'm.
approximate 1, right?
Say that again.
It's 1 almost, like 0.99.
For cosine of pi over 3.
Yes.
So if I substitute in cosine here, we actually get 1/2. It's from our unit circle. I believe it's one of those points where you would get like x and y is 1/2 and 1/2. And if I substitute in 0, what do I get? If I put cosine of 0, what do I get?
One now?
Nice. Yep, perfect. I've got 1. All right, so let's think about this for a second, though. I'm going to take a step back. We already know what this integral is, so I'm actually just going to write it down here. But if we change our bounds, we get 1/2 and 1. Can we do this? Can we do this integral? Or what do we need to do in order to make our lives easier with this integral? So if we recall back from Calculus 1, and I believe even like week 1 of y'all's course, the fundamental theorem of calculus says that if I have a larger bound on the bottom, I can flip the integral and add a negative sign. So then I get 1, 1/2, and then this becomes negative. And so all I need to do is add a negative sign to my natural log here. And then we evaluate this on the bounds from 1/2 to 1. And then the next step would just be to plug in our bounds. So I get negative natural log of 1 minus minus is a plus, natural log of 1/2. And if you guys want, we can finish this one out and I can give you guys an answer, or we can leave it as is. What do we want to do? Leave it as is? I like the sound of that. Sounds good. And for anybody that was curious, just in case, I'll throw it at y'all real quick. Oops, sorry. This is 0. This is the negative natural log of 2. And so negative natural log of 2. So then the answer would actually just be negative ln of 2. But this is perfectly fine, and this will be accepted on y'all's test, from what I understand. Okay. So I've got one more substitution example that I want to cover. And I'm going to get a fresh page here. And so this time, it's going to be a little different. It's not going to be as straightforward. I have the integral of x cubed square root 1 plus x squared dx. Oops, my u term, my du term, and my dx term. What is our u term? Nice. 1 plus x squared. Thank you, Luis. And then the derivative of this will be 2x dx. Nice, thank you, Bianca. And then this makes dx equal du over 2x. Substituting this back into my integral, x cubed square root of u du over 2x. And then I'm going to rewrite this really quick, giving me the integral x cubed square root u du over 2x. What can we do here? How do we deal with our variables here and here?
And we leave 1/2 outside the interval.
Okay. So then I'm going to get rid of this 2 in front of the x. What's next? What else can we do?
Can we just cancel one of the x?
Nice. Cancel, cancel. Leaving this as 2. So I'm going to clean this up. This is x squared. Okay, so how do we deal with this term now? Nice. Thank you, Camden. Okay, so if we notice, I have an x squared, and then in my u term, I also have an x squared. So I can solve for I can solve for x squared, meaning that x squared equals u minus 1. So rewriting that, I get u minus 1 times the square root of u du. Okay, so really quick, I am going to change it up a little bit for y'all. So I've got u to the 1 minus 1 times u to the 0 times u to the 1/2. How did I solve for u? Are you asking about this term, Luis? This one here? Yeah? Yeah, so what you can always recognize that we used this term here as our u, and we do have this x squared, and so we can actually just isolate it to let x squared equal this term, and it's completely valid. It's kind of the nice thing about substitution. Okay, so the next thing I want to do is I'm going to distribute this u to the 1/2 into this parentheses. So what would that look like? What do I get? I'll give you guys a hint. I'm going to get u to some power minus u to some power. Do we remember how to? Almost, Earl. Almost. Really close. So this is technically 2 over 2. So just to give everybody a little algebra recap, if I have a to the n times a to the m, thank you, Bianca, I get a to the n plus m. And so in this case, I have the same base, u and u. So I would get u to the 3/2. And then here, same thing, I have 1/2 plus 0, giving me 1/2. All right, and then du. So the next thing we need to do is evaluate our integral. So then I get, what do I get for this term? I get something to the something over something plus 1 minus u to the something over something plus 1. what do I get here? And then what do I get here? Okay, so I get 3/2 plus 1, 1/2 plus 1. Carrying that to the bottom, I get 3/2 plus 1, and then 1/2 plus 1. So what is this number? And then we did this one earlier, so I'll give you guys this one. 3/2, and then 3/2 becomes 2/3 u to the 3/2. And then now I'm just looking for this term here. Thank you, Jacob. 5/2 over 5/2. And then cleaning this up, I get okay, we'll talk about that in a second. Oh sorry, 2/5 u to the 5/2. Yeah. All right, and so one thing that we forgot, one thing we left behind was this 2.
The 1/2, right?
Right, exactly. Thank you. All right, so I'll go ahead and add that right here. And then in this case, we don't have any bounds. So I can drop this integral sign and we can deal with this 1/2. So what is 1/2 times 2/5? Plus C. Thank you, Luis. 2/10. Nice. And I get 2/10 u to the 5/2 minus, and then 1/2 times 2/3. Nice. Thank you. Thank you, Earl. I get 2/6. All right, so we can reduce both of these fractions, giving me 1/5 u to the 5/2 minus 1/3 u to the 3/2 plus c. And the last thing we need to do is substitute in our u, which again was this term up here, 1 plus x squared. So if u equals 1 plus x squared, this expression evaluates to 1/5. 1 plus x squared to the 5/2 minus 1/3, 1 plus x squared to the 3/2 plus c. Nice. We all good? We're still on the same page? Okay. So the next thing I'm going to do, we've got an area between the curves problem. And so the first thing I'm going to do before I draw it for y'all, I want y'all to draw it yourselves. The functions given are y equals x squared and x equals y squared. So go ahead and take a second to draw that into your notes. If you have to look at Desmos, please feel free. I am not too sure what it's going to look like on y'all's exam, but they're either going to be easy to draw parent functions, or if it's a complicated function, they'll give you the graph. So don't be too worried about your artistic abilities. I'm not very good at drawing either, so. Right.
Do we also need to graph y squared?
Yes. And then go ahead and just give me like a thumbs up or some kind of a something to let me know that we're all good to move on. I don't want to move on too quick through these. Cool. All right. So this is going to look something like, oops, pen is off. There we go. Shapes, graph. The purple curve is going to be my x squared. Actually, I'll draw it a little lighter. X squared, and then y squared is going to be in green. It's going to look like this. Should look something like this, right?
Yes.
Cool. All right, so the first part of this question, how do we, we're going to integrate this with respect to x. So what is the first thing that we need to do? Given my two functions, x squared and y squared. Top minus bottom, almost. So if I did top minus bottom, and I drew my vertical line, right? You see we would hit y squared and then x squared. But if I set that up in an integral, y squared minus x squared dx, right? We're rotating this, or we're taking it with respect to x. What happens? Are we quite at this level yet where we can deal with this? It's not impossible, but for the scope of this class, what do we need to do? And cool, we've got my graph, so I'm gonna get rid of this one real quick. Delete. Rewrite. Thank you, Jacob. Just gonna use my mouse. Okay. All right, and so if I rewrote this in terms of y, I would get y equals square root of x. Very nice. Okay, and so to mark up this graph a little bit better, I have square root of x right here, and then I have x squared. All right, and so before we go to the top minus bottom, there's one more step that we need to do. Right? We need to determine our bounds of integration. We know that we're starting here at x equals 0, and we see that we go all the way to x equals 1. But if we didn't have the graph, how would I do this? How would I find these 2 points? Thank you, Luis. Yeah, perfect. Yeah, we need to get everything in terms of x first before we can integrate with respect to x. So go ahead and keep this here because that's correct. How would we find our bounds of integration? Nice. And so we get square root of x equals x squared. And what we can do, little algebra trick, I'm going to multiply both sides. Or I'm going to square both sides, rather. Square both sides. And so it gives me x equals x to the 4th. And we know that this, at least, well, I know, but this equation is only equal at 0 and 1. Right? So plug in any value, let's say 2. If I had 2 equals 2 to the 4th, anything outside of 1 and 0 will not hold. So we get 0 to 1. And then now we've just got to evaluate our integral. So integral from 0 to 1 of x to the 1/2 minus, and then do you guys, I'm not too sure, depending on how y'all's professors teach them, I like to kind of distribute my integral across, or would y'all rather just keep this as one integral? Either way is fine. One integral sounds good. Okay, x squared dx. All right, so what do I get for this expression? So very close, Jacob. We just don't need to use u sub in this case. That's correct, Luis. We would use the power rule. So plus 1 over 1/2 plus 1 is 3/2. And then I'll rewrite this down here. And then this one should be straightforward. We should know how to do that one off the top of our heads. 0 to 1, x 3 over 2, 2 over 3 minus, and then this expression. One over 3, x to the 3rd. And then I can get rid of this, put a bracket, and then my bounds of integration are 0 and 1. So substituting in 0, we know we're going to get 0 to both for both expressions. So then substituting in 1 for both of these, I get 2/3, 1 to the 3/2 minus 1/3 x to the 3rd, or 1 to the 3rd rather, just giving me 2/3 minus 1/3 equals 1/3. Cool. You guys still with me? So the next part of this problem, I'm going to take those same expressions using this same graph, but now I want to set this up with respect to y. All right, so what is the first step here? I'm going to have you guys walk me through this one since it's super similar. What is step one?
Get everything in terms of y.
Nice. Very nice. So we've got x squared equals y, which means x equals the square root of y. All right. And so in this case, looking at our graph, if I draw a quote unquote horizontal line relative to the x-axis, where would I be drawing that line from? Left to right or right to left? Thank you, Luis. Very nice. So we go right to left, and the way you can think of this is that I have, let me get rid of my marks real quick. I will Is there a rotate button? Let's see if this works. Sorry, 1 second, guys. Okay, well, I can't rotate it. If you rotate the graph 90 degrees counterclockwise, you'll see that drawing my horizontal line in this case comes down like this, and we hit the red line first and then the blue line. So what is the setup of our integral? We have the integral of top minus bottom, or in this case, right minus left. What is our rightmost function? Thank you, Jacob. So I get, and then square root y minus y squared dy. All right. And the next thing we need to do is evaluate this integral. How can I tell? So remember, when we're integrating with respect to x, we can draw a vertical horizontal line, or I'm sorry, a vertical line. Sorry, a vertical line, and we hit the blue line first, and then we hit the red line all the way through. When we integrate with respect to y, like you said, we're drawing a line from right to left. So I'm gonna go here, and then you see I hit this function first, and then I hit the blue function. The idea here is that I've rotated my graph 90 degrees counterclockwise. Counterclockwise, for whatever reason in math, is the positive direction.
so whenever you think about rotating things, you don't want to rotate them clockwise because then you'll get a completely different scenario. And so for our case, orienting things 90 degrees counterclockwise gives us that the red line is our now top function, right, rather than our rightmost function, and that the blue line is now our bottom function. That kind of makes sense? Nice. All right. So now, what is this expression? Evaluating this integral, what do I get for this term? Nice. So using the power rule, we get y to the 1/2 plus 1 over 1/2 plus 1 minus y squared plus 1 over 2 plus 1. And you'll notice I've been doing this for every step. I kind of just want to emphasize when you're learning calculus, it is really good to do the extra steps to make sure you don't miss anything. Just kind of a food for thought. I have in my own experience, when I was learning calculus, skipped these steps, and that's typically when I made the most mistakes. So just kind of a recommendation. If you feel you don't need it, then more power to you. I'm kind of glad you're already at that position in your calculus skills, but if you're not, I recommend always writing the extra work. It only takes a couple of seconds. I promise you're not going to run out of time. So next we get and then we'll talk about that in a second. Y to the 3/2 over, and not over, 2 over 3, or yep, minus 1 over 3 y to the 3rd. And then one thing we forgot to talk about is what are my bounds of integration and how would I solve for them? It's the same approach. I just kind of want to see if we remember. Yes, that's correct, Jacob. It'll be recorded. I'm not too sure when it's going to be posted. Hopefully, I'll be able to post it on the Canvas page pretty much as soon as I'm done. But I do believe we're like in the process of building a playlist for 1223 at least. And so whenever those videos start getting posted to the YouTube channel, I'll make announcements about it. If you have to go, yeah, please don't feel like you have to stay. This is going to be recorded and posted later. Of course, thanks for coming, man. All right, so how do we solve for our bounds of integration? At the moment, Bianca, I am not too sure. I am still waiting for things to be posted. So as soon as I have the links, you guys will get them as well. But depending on who your professor is, I will find them as well. The previous TA, nice, thank you, Luis. The previous TA also had a playlist, and so I'll find those links and make announcements about them later on, just so you guys don't have to wait around. I'm not too sure when the math office is going to get to that. So, all right, and then so what are our bounds of integration? I didn't do the Cal 1 videos, but I was the UTA for Cal 1 last semester. So if you ever attended my targeted workout sessions, that's probably where y'all recognize me, if you do. And then, so what do we get here? And then what do we get here?
No, it's also 0 to 1, right?
Nice. 0 to 1. All right, and then same thing as before. 0 into both of these expressions gives me 0. 1 into both of those expressions give me 1. So then I end up with 2 over 3 minus 1 over 3, which equals 1 over 3. All right. Okay, so the next one we've got is a volume example. We're going to move on from area between curves. Does everybody feel pretty confident about area between curves, or would you guys like to see another example? Another example? Yeah, of course. Give me 1 second. Let's see. Okay, cool. So the next one I want to do is y equals x squared minus x cubed plus 1. Oh, sorry. Let me close that parentheses real quick. Close the parentheses plus 1. And then y equals 1. Yeah, that's fine. So I'm going to give you guys a second to graph that one, and then we'll talk about it. Go ahead and give me a thumbs up when y'all have graphed it. So with the graphs, so right now I'm encouraging y'all to use Desmos for the sake of visualization. But for your exam, they're either going to be straightforward parent functions like linear functions, horizontal vertical lines, or parabolas, or if it is going to be a complex graph, like a really difficult graph to visualize, they should give it to you. They should. So just make sure you know how to draw a parabola and you'll be okay. All right. I'm gonna go ahead and post this in here. Actually, go ahead and give me a thumbs up if we're good. Cool. Cool. Bianca, Victoria, we good? Cool. Victoria,
Yes.
cool. So you're gonna get something that looks like this. It should move in a second. There we go. All right. So this is the function that we're dealing with. What is, so I guess let me go ahead and kind of make a little checklist for y'all. So the first step, the second step, the third step, and then we'll add more steps if we need. So the first step can be anything, to be honest with you. We have a lot of options. I'm gonna go ahead and let you guys decide what you want your first step to be. Do we want to solve for our bounds of integration? Do we want to try to set up our integral? Do we want to do the horizontal line test?
I'll say horizontal line and then the bounds of integration.
Okay, cool. So we're gonna go, first step is decide what is top and then what is bottom. So then in this case, our horizontal line, we hit this nice function and then we hit our horizontal line, making, oops, x squared minus x cubed plus, oops, close the parentheses, plus 1, and then y equals 1. All right, and then bounds of integration. Or what do you guys want to do next? Seems to be just y'all now, so you guys kind of get to dictate the flow of the rest of this study session. Bounds, awesome. So we're gonna go ahead and get the bounds. And then, so how do we do that? So that way I can include that in my notes. Cool. Set. To each other. All right. And then what do we get? On your exam, it's definitely not going to be this hard. You're definitely not going to get x squared minus x cubed plus 1 equals 1. So feel free to use a calculator if you need for this case, because this is going to be a little weird. You'll get a clean number, but the process is a little confusing. And I don't want to bar you guys with those details because you're not going to need them. Sorry. Okay, nice. So we do get 0. We get 0 as one of our bounds. What is the upper bound? Minus 1? Nice. And 1. Cool. Okay, so I'm going to go ahead and kind of go through our steps here. So we've already talked about our bounds. And we've already decided that x squared minus x cubed plus 1 minus 1, right? Because this is top, this is bottom. So then what is the next step? So I can include it in my list here. Power rule. Okay, cool. So we're going to go ahead and evaluate our integral. Evaluate. Nice. Okay. So we get x squared plus 1 over 2 plus 1 minus x cubed over 3 plus 1 plus 1 plus 1 x to the 0 plus 1 over 0 plus 1 minus x, oops, 1 x to the 0 plus 1 over 0 plus 1. And then taking a step back really quick, since this entire expression is included in our integral, if we wanted to, we could cancel this. Are you guys okay with me doing that? Cool. And then in this case, we are with respect to x. Okay, so then this becomes x cubed over 3 minus x to the 4th over 3 on the bounds from 0 to 1. In this case, oh, sorry, to the 4th from 0 to 1. Again, 0 in gives me 0, 1 in gives me 1. Can you cancel the 3s and the 4s? Are you saying, can I cancel these? Or are you saying these? The powers or the fractions? The power and the denominator? So not quite. So same base, but in this case, we're subtracting. And so the rules for exponents are a little bit different for addition and subtraction compared to multiplication and division. So what I think you're thinking of is if I have, like before, a to the n times a to the m equals a to the n plus m. And then for division, we get a to the n over a to the m equals a n minus m. I think that's what you're thinking of. And then the denominators, we just can't cancel them because they're different. They're different bases. Yeah. So next, I'm going to substitute that in. So I get 1 over 3 minus 1 over 4. And then what is the next step to deal with fractions with different bases, with different denominators?
We can get them to the same denominator.
Nice. And then so I'm going to multiply this side by 4 over 4. And then this side by 3 over 3. Is this what you were getting at, Luis? Is this kind of what you were talking about? And then I get 4 over 12. Oops, I'm going to do that in black. Minus 3 over 12 equals 1 over 12. Okay. All right, and the next one I want to do really quick, I saw someone say 3 to the exponent over 3, they could cancel the 3s. Oh, so if I have like 3 to the 4 over 3, right? This is exactly the same as 3 to the 4 over 3 to the 1, which would give us this. Right, so then I would get, yeah. So then I would get 3 to the 4 minus 1, which is 3 to the 3. And the next one I want to do really quick, before we move on to volumes, is y equals sine x, and then y equals cosine x. For the range, or I guess where x is in 0 to pi. So I'm gonna go ahead and give you guys the range. Have a good one, Bianca. Thanks for coming. Go ahead and take a second to draw this, and then we'll talk about it. And then give me a thumbs up when you guys have drawn it. Did we get this? Yep, cool, perfect. Roberto, we good?
Yes, yes.
Cool, all right. So I want to talk about this one. We'll set it up, and then I will leave the rest of the integration up to you guys. The main thing that I want to cover here is how do we approach this integral? Or how do we approach this scenario? We know that we're going to have to do area between curves. We know we're going to have to draw our vertical line. But in this case, if you notice, our point of intersection is actually in the middle of the range of our x, right? So we'd intersect here. So if I draw my vertical line and I go here, right? I would see that cosine is my top function on this side minus sine, and then we would integrate, right? But can we just say this is our integral from 0 to pi? Is this all we have to do?
I actually don't remember. So
Okay, anybody? I'm gonna wait for the group really quick. Can you repeat the question? Yeah, so if I just say, and I look at this, and I got this on a test question, and I just put this as my integral, is this correct? Is this the correct integral? Or is there something we have to do? Nice, very nice. Can you tell me why? Sorry, I know you have to type that, but can you tell me why, Luis? And so Roberto, what Luis said is that no, this is not the proper form of our integral. Would you be able to also tell us why? Okay, yeah, we're missing dx, but there's one more thing. Sorry, we're missing dx. But there is one more thing, and there's a reason why this isn't our integral. We have to integrate. Okay, so if we look, right, we do get cosine over sine, right? That means this part is correct, but we see at the point of intersection, if I draw another vertical line on the right here, we actually hit sine and then cosine. So if we were to just integrate 0 to pi, we would be incorrect. Does that kind of make sense why? We would only get half of it. Technically, I think this actually evaluates to 0, which is incorrect, but you're like halfway there, Luis. So yeah, we would only get half of the integral. We do need another part of the integral, and the other part of the integral, nice, thank you, Victoria. The other part of the integral is here, 0 to some number of cosine x minus sine x. Right. Plus or minus here, Victoria.
Can you repeat the question?
So you were correct. Thank you, Luis. You were correct that the next part of the integral is going to be sine minus cosine. But is this plus or is it minus?
Will be plus.
Nice. Plus the integral of sine of x minus cosine of x. And then dx. And then this would be pi. I'll go ahead and give you guys this one. And then so I'm going to leave the rest of this as an exercise for you guys. It would be the same steps that we followed up here, where we found our top minus bottom, we set the equations equal to each other, and then we evaluate the integral. And in this case, you will get some form of k times pi over some integer n. But I'll let you guys solve that one because there is a possibility that this one will be on your test. So I don't want to solve it for y'all. But this is the general setup, and you just need to solve for this one, and you just need to solve for this one. This one and this one. Kind of makes sense. What I was kind of getting at is that we would need to split up our integral because we have a point of intersection here, and then the top minus bottom actually flips. Make sense? Cool. Everybody good? Okay, is that a I'm gonna take your word for it, okay, or is that a I'm good, okay, Luis? Okay. All right. So moving on. I'm gonna bring back one of the problems that we did a second ago, but now we're gonna do a revolution about the x-axis. So we're gonna do some volume integration here. So I've got y equals x squared and x equals y squared. And then I'm gonna copy that graph here. Nope, it's not gonna work. Picture this device, this one. Actually, put it right here. Okay. All right. So is this a different? Yes. So this time we're going to do volumes instead of area between curves. So it's going to be a pretty similar setup. But I'm going to go ahead and give you guys a little brief introduction into what's going on here. All right. So if I take this graph and I revolve it around the x-axis, right, I'm going to get little volumes that look like this. Right? And then I'll do it in green here, where I get this. Right? We agree? Yep, cool. All right. So first off, what is the technique we're using here? Are we doing shell method, washer method? Are we just doing volumetric integration? What are we using here? Okay. Everybody agree? Nice, cool. Washer method. All right. So what is the formula for washer method? It's very similar to our area between curves. It's just a little different.
This one is the same as this method, right?
Similar, we're using a washer method this time. Nice. Nice. Okay, cool. So I think both of you guys have the kind of general idea of what I was looking for. You're correct. We're gonna have pi. And then like Luis said, we have r squared. But what is r squared in this case in terms of the washer method? Uh, Almost. You're halfway there, Luis. So remember, we have two functions, and remember for area between curves, we have top minus, oops, come on, minus bottom, right? And so we can do something kind of similar, but the terminology that they use is outer minus the inner, right? Because we have two radii in this case. We have the outer radius and the inner radius, right? So that forms our washer. And then what am I missing from this equation? I'm missing two things inside the parentheses. Nice. So then squared and squared. Okay, and then I think we were kind of already heading in that direction. So if I do another vertical line, we're doing this about the x, so I want all of my terms in terms of x. So this equals y equals square root of x, right? This is square root of x. This is x squared. And so what is my outer radius? Drawing a vertical line. I'll use pink. What do we get for this? Okay, so it's going to be the same approach to area between curves as far as determining what's your outer and what's your inner radius, right? I'm going to draw my vertical line, and whatever I hit first is going to be my outer radius, and then whatever I hit second is going to be my inner radius, right? So in this case, we hit x, or square root of x first, and then we hit x squared. So filling that in, we get pi integral of square root of x, come on, x squared minus x squared squared, then all of this times dx. Okay, the last thing we need to do is we need to talk about our bounds of integration. And why did we do that? Why is this the outer radius and this the inner radius? Is that what you're saying? How did I set that up? Okay, watch. So I'm gonna clean this up a little bit. So you remember from area between curves, if this wasn't a volume question, we would just draw a vertical line, and then I would say that x squared or square root of x is my top function, and then x squared is my bottom function. In this case, it's exactly the same. it's the same approach. It's just this time, instead of taking this area minus, oops, give me green, minus this area, right? I'm drawing volumes in the shape of some circles. And so I get this, right? And I'll do it right here. This. And then if you watch, here's the inner radius right here. Oh, I'll draw that a little better. Right? And so we get a little bit of a washer, right? You kind of see the washer formed there. Cool. All right. And then so now we just need to talk about our bounds of integration. And again, it's unfortunately given to you, but how would we do that?
It's going to be also setting equal to.
Nice. So then I get x squared equals square root of x. And again, our bounds of integration are 0 to 1. And so 0 to 1. And then I'm going to go ahead and send these square terms into the parentheses here and here. So then I get pi integral x minus x to the fourth dx. And then we're going to go ahead and use the power rule. So then I have x to the 1 plus 1 over 1 plus 1 minus x to the 4 plus 1 over 4 plus 1, giving me x squared over 2 minus x to the 5th over 5 on the bounds from 0 to 1, 0 to 1, all of this times pi. All right, and then I'm going to pause here and I'm going to let you guys finish this one. Let me know what you guys get.
Is it pi over 2 minus pi over 5?
So you got pi over 2 minus pi over 5. And then there's one more thing we need to do. I'm going to find a common denominator. This would give me 5 pi over 10 minus 2 pi over 10, which is very nice. We get 3 pi over 10. Very nice. Very nice. Okay. The next one, we're going to get y. Either way is perfectly fine. The way I think Roberto did it is he already solved, you get 1 over 2 minus 1 over 5, and then he put the pi in, I think, right? And then that's where you get pi over 2, 5 pi over, and then pi over 5. And then either way, it's exactly the same from finishing this step up. Yeah. Okay, nice. So the next example, y equals x squared. and y equals 2 minus x. Go ahead and draw that, and then give me a thumbs up when you guys are good. Thumbs up, nice. Okay. So here, get nice. Right, so the picture is going to take a second to load. And so this time, what we're asked to find the volumes of the solid found with squares perpendicular to the x-axis, right? And so what that looks like is I want to be perpendicular to my x-axis here, and then I'm going to draw squares. Hopefully this looks good enough. We kind of see what's going on here. We're getting volumes that are formed by these squares. Kind of makes sense what's going on here.
Why are we drawing squares?
So they are perpendicular to our x-axis. And then if we look at a side view, this is our side view. The squares along that region are going to kind of boom, 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 boom. I just didn't want to make it too messy because these tend to get really, maybe I can redraw these real quick. Boom, 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 boom. So you see we've got the base of the square perpendicular to our x-axis. And then, dang it. Here, and I'll draw one more. They're kind of protruding upwards into the Z. Again, art is not my forte, so I apologize if this looks a little rough. But I'm sure you guys have seen these examples in WebWork, and WebWork definitely does much better at drawing them than I can. We kind of see what's going on here, though.
Yeah, okay, I get the point.
Yeah, okay. All right. And so the first thing we need to do is we're finding volumes using squares. So the first thing is, what is the area of a square? What is this formula?
Just the length times the width.
Nice. Length times width. And in this case, because it's squares, I'm just going to go ahead and say side squared because they're the same. Length and width will be equal. Okay, so how do we find the side length? What would we do? If it's not immediately obvious, it's okay. I don't mind explaining it. I just want to see if anybody. If we want me to just explain it, go ahead and just give me like a thumbs down or something. Something that's not a thumbs up. Okay, sounds good. All right. So in this case, because we're doing squares perpendicular to the x-axis, we do have the beauty of taking advantage of our horizontal line test. And so in this case, I'm gonna write these in purple. I've got 2 minus x squared here in green, and I've got x squared here in blue. And what I'm gonna do is I'm gonna draw my horizontal line test. And you see that we hit 2x, or sorry, 2 minus x squared, and then x squared, right? So it would be a pretty similar situation to top minus bottom, only in this case, the difference in these two gives me this side length here. That kind of makes sense? Kind of, sort of, maybe no? Can I repeat that? Yeah. So we can take advantage of the fact that one, we're using squares for our cross-sectional volumes, and two, we know that using a horizontal line, right, we can find our top minus bottom. And then so all we need to do is find the distance between these two functions, 2 minus x squared and x squared, which is exactly this distance here, right? And so the way we find that distance is we actually just subtract them from each other. So side 1s equals 2 minus x squared minus x squared, which gives me 2 minus 2x squared. Make sense? Everybody caught what I said? Yeah, cool. Cool. Howdy, Ireland. Roberto, you kind of understand what I said?
Yes.
Cool. All right, so Ireland, just to catch you up real quick. So we are asked to find the volumes of squares found by perpendicular cross sections to our x-axis, and so that's what I have going on here. The two functions that govern our region are y equals 2 minus x squared and y equals x squared. And then we just found this side length here. We just solved for s. And the way that that works is we can take advantage of the fact that we can use our horizontal line test, and any horizontal line test that we draw from this point to this point, or this point to this point, is the length of our side. And so the way we find the distance between two functions is we just subtract them from each other. And so that's what I have going on here. So I'll give you a second, Ireland, to write everything down, and then we will go from there. And while Ireland is getting caught up, what is the next step that we need to do? Right, now we found area, right? So our area is given by side squared, which is 2 minus 2x squared squared. And then foiling this expression, we get 2 minus 2x squared times 2 minus 2x squared. And if we remember, we go 2 and then 2 times 2x squared, and then we get here and then here. And so carrying that out, I'm going to get 4 minus 4x squared. And then doing this term now, I get minus 4x squared. And then these two would give me plus 4x squared, 4x to the fourth rather, sorry. And then I can combine like terms. 4 minus 8x squared plus 4x to the fourth. Okay, so this is my area of one square, right? This polynomial here gives me the area of one square. But how do I find the volume? What do I need to do?
Do we still need our bonds of integration?
Right. So I was going to talk about that next. I just want to go ahead and kind of get in the direction of where we need to go for this. And so how do we go from area to volume? But you're correct. You are
Well,
correct.
we'll need to multiply it again, right?
What do you mean?
Like the term, like in a square is just like the length times the width. So we're gonna need to add another one, right?
This part here? So
Yes.
that's what we did here, in this part here, right? This is my side length, which is one of them, and then I squared it, which gives me this. Make sense?
Okay, okay.
Yeah, okay. So then the next step, right? In order to go from area to volume, we need to integrate our area with respect to, in this case, it'd be x, right? So I'm going to go ahead and integrate 4 minus 8x squared plus 4x to the fourth dx. And then now we can talk about our bounds of integration. So what do we do? How do we find the bounds of our integration?
You need to turn them into y equals and
Okay, so you're saying what I
like
have up here, right?
equal to each other.
Very nice, very nice. So I get x squared equals 2 minus x squared, right? And then what do we get for our bounds of integration? Do you guys want me to walk you through this algebra?
One is gonna be 1.
Uh-huh. And then one more. You need your left bound. Not quite. So -1. Thank you, Victoria. So real quick, Luis. So I've got this term. I'm going to rewrite it up here. If I move that x squared to the other side, I get 2x squared equals 2. Right? I can divide by 2. X squared equals 1. I take the square root of both sides. So then x equals plus or minus 1. And so that's where we get these terms. Make sense? Cool. All right. So rewriting this expression down here. Copy, paste. I get -1 to 1. And then we're going to go ahead and use the power rule. So then I get 4x to the 0 plus 1 over 0 plus 1 minus 8x to the 2 plus 1 over 2 plus 1 plus 4x to the 4 plus 1 over 4 plus 1. Oops. Come on, there we go. And then rewriting this, we get 4x minus 8 over 3x to the third plus 4 over 5 x to the fifth, all on the bounds, -1 to 1. And then I'll let you guys finish up and let me know what you guys get. while I'm waiting, I'll go ahead and start writing it down. I get 4 times 1 minus 8 over 3 times 1 to the third plus 4 over 5, so 1 to the fifth, minus 4 times negative 1. Drop the thickness real quick. Minus 8 over 3, negative 1 cubed, plus 4 over 5, negative 1 to the fifth. All right, this gives me 4. Thanks for coming, Luis. Have a good day, man. 4 minus 8 over 3 plus 4 over 5. Sending this in, this would be negative 4. This is plus because of this negative cubed. It still stays negative. So then I get 8 over 3. And then again, because of this negative and an odd power, we still get minus 4 over 5. And then sending this negative across to all of my terms in the brackets, I get plus 4 minus 8 over 3 plus 4 over 5. And then I'm going to find a common denominator, which in this case is 15, right? So I get 60, yes, over 15 minus 40 over 15 plus 12 over 15, and then again plus 60 over 15 minus 40 over 15 plus 12 for 15. Rewriting this, we get 60 minus 40 plus 12 plus 60 minus 40 plus 12 all over 15. Okay, I'm going to combine 60, 60, negative 40, negative 40, and then 12 and 12, just to kind of chop up the work that we have to do. So I get 120 minus 80 plus 24, all over 15. Gives me 40, this is 40, and then plus 24, I get 64 over 15. Yeah. We agree? Did I move too fast?
No, I got the same answer.
Same answer? Perfect. Victoria, Ireland, we good?
Yes, thank you.
Cool. Sounds good. All right, and I'm gonna do, hopefully I have time for a couple more, but we will see. I'm gonna give you guys a shell method just to make sure that I at least cover all of the volume ones. And then tomorrow during the 1224 one, I'll make sure to cover physical applications, and then we'll go from there. So this next one is y equals x squared minus x, and y equals 0, and we're going to revolve about, oops, not Abbott, about the x. Okay, so I'm going to go ahead and give you guys a second to draw that, and then go ahead and give me a thumbs up when you guys have it drawn.
Okay, this is kind of off topic, but not like off topic, but how do we know what method is easier again whenever we do shell and washer? Because shell is with X, no, it's with about the y-axis, right?
About this case is about, so either method is valid. Thanks for coming, Victoria. Either method is completely valid. They will tell you what axis you're integrating with respect to, or like in the case of the squares, our squares were perpendicular to the x-axis, so we'll be integrating with respect to x because we're like here, right? Our squares are moving across the x-axis, so we're integrating in this direction, right? Which is our x-axis, it's x. So
Okay,
I
makes sense.
guess in the general sense of your question, they'll make it obvious, right? One, they'll make it obvious what method you'll have to use. I believe it'll be explicit. It'll be explicit, like you're going to use the washer method, you're going to use the shell method. And then again, they'll tell you exactly what axis you're integrating with respect to.
Okay, thank you.
Mhm.
And then this is like another question to build off that. Whenever they give you, you know how they give us the formula, obviously?
Mhm.
So if they only give us one function, we can assume that we don't have to plug in the other one, right? Like, for example, in the shell method, since it's radius minus the height, but there was some examples where they only gave us one function. We assume our radius is x sometimes, and then, you know what I'm
So
trying to say?
not necessarily x, but I believe like, so in the case of this question, right, we're asked to find the volume formed by the region enclosed between x squared minus x and then y equals 0, right? So when you do like top minus bottom or left minus right, you won't necessarily have to include this in your formulation. Kind of makes sense?
Okay, yeah, that makes
Yeah.
sense.
Okay, so this is a shell method example. And so we're asked to find this little bit, and then it forms a cylinder. I'm gonna try to draw this nice and clean. And then we're gonna get a little bit of a bigger shell here, and a bigger shell here. I'm gonna draw 3. Hopefully it doesn't get too messy. I'll draw one of the bigger ones in the middle here. So if I do this, and then this, we get this. And then our shell is gonna kind of cascade downwards like this. We're gonna get a like a shell kind of, like an actual shell kind of a shape here, like a seashell or something. Kind of makes sense? I hope that picture wasn't too messy. All right, so do we remember the formula for the shell method?
Yes, it's v equals 2 pi, the
Mhm.
integral from a to b, and then radius times the height dx.
Okay. So in this case, though, instead of saying radius, what do we use instead?
The x-axis?
No, so it would be f of x instead of r, right?
Oh, okay.
Makes sense? Then
That makes
dx. Okay. And then so this is what I was saying, kind of to your question, right? The only reason that x or y equals 0 is included is to let you know that we're doing this little motion here, right? But in this case, right, the only thing that's really moving, or if, yeah, the only thing that's actually moving in a revolution is this function, right? Our parabola, right?
right.
So knowing that, how do we set up our shell method formula? What do we need to do here? What do we need to change?
Well, we would substitute our function f of x
Yep,
minus the 0, which we don't need to include, but
exactly. Very nice. Oh, I'm sorry, we missed something here. So we're missing a term in our formula. You're very close. I didn't catch it, my fault. We're missing one thing. Do we remember?
our x.
Nice. Thank you. So we've got 2 pi integral x squared minus x, right? Dx. And then I'm going to go ahead and distribute this x, and then we'll talk about our bounds of integration. So we get the integral x cubed minus x squared dx times 2 pi. And then what would our bounds of integration be if I set x squared minus x equal to 0? What would I get?
Zero and 1.
Very nice. I get 0 and 1. All right. So then what is the next step here? What do we need to do?
Integrate it.
Very nice. So this term becomes x cubed plus 1 over 3 plus 1 minus x squared plus 1 over 2 plus 1. And the bounds from 0 to 1 times 2 pi. All right. Cleaning this up, I get x to the 4th over 4 minus x to the 3 over 3. Sending in 0 gives me 0. Sending in 1 gives me 1. So I get 2 pi, 1 over 4 minus 1 over 3. We agree?
Yes.
Cool. And the last thing I want to do before I send in my 2 pi is find a common denominator and solve for this expression here. So I'm going to multiply this by 3, multiply this by 4 over 4. This gives me 3 over 12 minus 4 over 12, which gives me negative 1/12 times 2 pi. So then we get negative 2 pi over 12, which reduces to negative pi over 6. We all get the same answer?
Yes.
Yeah? Okay. Roberto, are you good?
Yeah, I was taking a little longer, but yeah, thank you.
Yeah, of course, of course. Did you have any questions about this, both of y'all?
Yes. Okay, so this is what I was a little confused about.
Mhm.
In the formula, where does the x come from? Is that not our radius?
This extra x here?
Yes.
So the formula for the area of the surface area of a cylinder is SA equals 2 pi height times radius, I believe. You get and then so x will always be this distance here, right? And so depending here, right? And then our radius is actually, I'll draw it the other way so you can see. Our radius is our f of x, right? Because we hit the f of x line. And then we get the height here. And then the dx term is actually the thickness of the shell. So from this distance here, right? The distance between the two shells is our dx. Kind of makes sense?
So then our height was our function minus the 0?
No, so our height is just x. The
Oh.
radius,
Mm.
right, is the function minus 0. Or this, yeah, f of x. In this case, minus 0.
Oh, okay, thank you.
Yeah, no problem. Cool. So that concludes today's Zoom session. I didn't get to cover as much as I wanted to, but like I said, I'm doing 1224 reviews tomorrow. And for them, they cover some additional topics. So I'll make sure to cover physical applications there as well. So yeah, feel free to either come by. It'll be 6 to 8 tomorrow in the evening, or as soon as the recordings are posted, I'll make sure that they get out to y'all. So I'm gonna go ahead and stop this. And
So-
thanks for coming, you guys. I appreciate it. You guys
Thank
have
you
a
for your
wonderful rest of your
time.
day. Of course.
Okay,
The one for
bye.
tomorrow will also be recorded, right?
Yes. And so as soon as it's posted, I'll let you guys know where.
Awesome. Thank you.
Cool. Have a good day, guys.
Likewise.